Okay, let's start. So I want to start by talking about Bose-Einstein condensates. But at first, let's just talk about a couple of philosophical points. So what is Bose-Einstein condensate? Bose-Einstein condensate is a macroscopic quantum phenomena, and it is not the only example of macroscopic quantum phenomena. There are other examples. For example, superconductivity, superfluidity, quantum magnetism, quantum Hall effect, and the list just goes on. And there are many other examples, and my goal is to go through these examples. And for us to be able to observe these phenomena, we require some conditions. First of all, we need low temperature. And typically, the temperature domain of all of these effects is like order of 1 Kelvin. Maybe in some special cases, like for example, high TC superconductors, it can be all the way up to like hundreds of Kelvin, but typically even 100 Kelvin is small temperature for us. 1 Kelvin, sometimes micro Kelvin, and in the case of like an atomic ultra cold gas, we need like nano Kelvin temperatures. So we need 1 Kelvin or lower temperatures, because at high temperatures, effects of quantum mechanics are washed out. If you want, they are like average out, because quantum mechanics is generally fragile and we don't see it in our everyday life. The second requirement is a large number of particles. And this is like, you can think about Avogadro's number. And having a large number of particles is not sufficient. We also require them to interacting particles. Because if they are not interacting, we have like a non-interacting gas, and non-interacting gas can be reduced to like single particle phenomena. So we need interactions. That's why we call this a many body, actually, because it's like quantum, first quantum, and then many body phenomena. These are requirements for us to see these things. And you need to compare this with what you learn in undergraduate quantum mechanics. In the undergraduate quantum mechanics, we have like a single electron in a box. That is like a single body problem. Or we have the harmonic oscillator. We have just like an oscillator and it just holds a single particle, right? There is nothing else. Even in the hydrogen atom, we have like a proton and electron, but we just say that so-called Born-Oppenheimer approximation, proton is much heavier than electron, so proton we can assume it to be stationary. So it's like a single body in the field of a Coulomb potential. So let me give you a history of the phenomena that have been observed so far. Let's go through a brief history, which will serve us kind of like an outline of this course. I think the first experiment that initiated all of these things is probably like Kamerlingh-Onnes in 1911, and observation of superconducting mercury, and the temperature he found that was 4.1 Kelvin. Of course, at the time, nobody had no idea what it was, but it was like a completely unexpected result, and it was the beginning of all of these nice manifestations of quantum mechanics. In 1925, Bose-Einstein condensate was predicted theoretically. And the story goes like Bose actually derived Planck's law by using mathematics and combinatorics, and he sent this paper to some European journals, and since he was a guy from like some unknown land, nobody took him seriously. And then he wrote a letter to Einstein saying, look, I derived what Planck derived, but in a better way, and Einstein recognized its importance. Also, Einstein generalized Bose's idea in a significant way, and then they predicted Bose-Einstein condensate. But it was not observed, and in I think 1927, lambda transition of helium-4 was found, and the temperature was 2.2 Kelvin. And it was kind of like observation of superconductivity, but it was a different system, right? Helium-4 is like a liquid you can put in a bucket and look at it. But like once the lambda transition take place, what you see in that bucket was completely different. It was the first superfluid that was observed, and we are going to spend some time why this is superfluid and what is the connection between this superfluid and the Bose-Einstein condensate. And at that point, I think people like recognize there's like a macroscopic quantum phenomena that needs to be understood. And one of the first theoretical formalism that explained many things about these systems came in 1950 by Ginzburg-Landau. I think it's my date, 1950. Formalism for superconductors. And this is called completely phenomenological theory. Basically, it is not based, of course, Landau was like a very influential person. He knew a lot about a lot of things. He had his intuition from microscopic physics. But the theory itself was not microscopic. It was like a phenomenological theory. And that's actually where you'll see many similarities with field theory. If you have ever studied like 5^4 theory, or like if you write like Dirac action with spins and so on, and you are going to see there are like many similarities between that formal mathematical treatment and the physical Ginzburg-Landau approach. Hopefully, we'll also spend some time, maybe in a couple of weeks, how to do this within the textbook. And up until now, like superconductivity was observed in 1911, and almost like 50 years passed, and many like influential people spent a lot of time trying to understand what's going on with superconductors. And I think the list has like, of course, Einstein, Feynman, Onsager, and there are many other smart people. They try to solve the mystery of this superconducting state, but nobody could do it until 1957. BCS theory came up. So this is a microscopic theory, and Ginzburg-Landau is phenomenological. So BCS stands for Bardeen. Bardeen is the lead, like the guy. He already had a Nobel Prize at the time from invention of transistors, and he was in Illinois Urbana-Champaign, and he had a postdoc, Cooper, and I think Schrieffer was his graduate student. I think he was sharing his office with his postdoc, and these three, he assigned this problem of superconductivity to these two. I don't know in how long, but they solved the mystery. There's like very influential paper by Cooper, which came up with something called Cooper instability, and a few years later there was like complete BCS theory, and BCS theory explained almost everything about conventional superconductors. And that's like a very important step. There are other things that happened, like for example, there's like Anderson coming up with like Higgs mechanism. Higgs mechanism actually first suggested by Anderson within the context of superconductors, and Higgs, being like a very smart guy, recognized that was also the case for particle physics. But let me not write those details. And the next step I want to pick that we'll have time to talk about is 1921 superfluidity of helium-3 at 2.8 microkelvin. So helium-3 is not like helium-4, right? You may, if you are not experienced, you may think like, oh, these are like same things. They are completely different things. There's like one is 3, one is 4. And the abundance of helium-3 is much orders of magnitude smaller than abundance of helium-4. And this is actually a byproduct of like nuclear proliferation. During like this nuclear arm race, people had a lot of byproducts in their like nuclear reactions. One of the rare byproduct was helium-3. Helium-3 is a fermionic isotope, whereas helium-4 is a bosonic isotope. And when you have like enough of it, you can do experiments. And people started doing it in 1970s. And of course, if you see a superfluidity in helium-4, you may also wonder if it is possible in helium-3, but it turned out to be much more challenging. One is a phenomena that happens around order of 2 Kelvin. The other one is like 1,000 times smaller temperature domain. I think this is much more complex, and the textbook is spending quite a bit of time on this towards the end of the book. Hopefully we may have time, if you have the appetite, we may talk about it, but we'll see. And the next step is okay, there are other things I'm skipping. Let me just write the biggest things. Actually, there is also here quantum Hall effect, but let me not get into that for the moment. 1986, high TC superconductivity in copper oxides. And the temperature was around the temperature elevated afterwards, but let me just write it like it was order of 100 to 200 Kelvin. Also in physics, I think you are probably familiar, the order of magnitude of effects already explains you that there's like a different domain, right? In the helium-4, you are order of 2 Kelvin, and the mechanisms, the physics, the theory is completely different if you go 3 orders of magnitude, right? Think about like atomic physics. Atomic physics is like electron volt, and once you go sub-electron volt, right? But so once you go much higher than electron volt, thousands of electron volt, you go to domain of nuclear physics. And typically, if you are like an atomic physicist, you don't care about nuclear physics because you don't see any effect of that. On the other hand, if you just increase the energy, you go to subatomic physics, right? You go to quarks and gluons and these things, and it's like GeV, much higher. And if you are studying GeV, quarks, gluons, and things like this, you don't care about nuclear physics, and let alone you don't care about atomic physics. So every time you change this order of magnitude shift in the energy, this tells you that there's like a different universe in front of you. There's like a completely different physical system. And here is also the case in the cuprates. When you have a superconducting experiment in hundreds of 200 Kelvin, it tells you it may not have anything to do with something happening in 4 Kelvin, because there's at least 2 orders of magnitude difference. I think the textbook doesn't have much about high TC superconductivity, but we can use other books to talk about it a little bit. But like I said, I didn't decide it yet, so we'll see how it goes. And lastly, okay, there are other things here I'm also skipping. In 1995, BEC, Bose-Einstein condensates of atomic gas observed experimentally. And the domain is like order of, let me call it 1 nanokelvin. So this is 10 to minus 9 Kelvin or so. And this development happened thanks to thanks to some revolutionary developments in laser physics and also magneto-optical trapping and things like that. And we are going to talk about that. So these are the list of things I want to talk at some point, at least in a phenomenological level. And if we have the appetite, maybe in a microscopic field theory approach. But I don't know if I can do that at the moment. We'll see. And I want to also add some honorable mentions. So for macroscopic quantum phenomena, there is something called phonons that most condensed matter field theory books start their treatment with phonons because phonons are very easy, right? Even a third year or even in a modern physics class, you can teach phonons because these are kind of like photons, but they're a little bit different, right? Photon is like an electromagnetic oscillation. Phonon is quantization of crystal vibrations. And you can see quantum effects in phonons by, for example, measuring specific heat of a piece of substance. But the reason we start with this is you can reduce phonons. Phonons are these lattice sites are connected to each other with strong springs, but you can do a set of mathematical transformations to reduce the problem to a non-interacting problem. It's like a non-interacting Bose-gas problem. And then that explains why specific heat is so-called T-cube law and so on and so forth. We may talk about this, but I think it is going to be a little bit of sidetrack. Second, so this is also macroscopic quantum phenomena. You have a piece of material in your hand, you make a measurement on it, and it tells you about quantum mechanics. Whereas in microscopic quantum mechanics, for example, in hydrogen, you need a very detailed macroscopic experiment. You need spectroscopy, or you need very good resolution, so on and so forth. A second honorable mention that we may or may not talk about is quantum magnetism. So take a piece of magnet in your refrigerator and look at it. It's actually a macroscopic quantum system, right? If we didn't have quantum mechanics, you wouldn't have magnets. So that's the message. And the book, at least James Annett doesn't have it, but Gerwin and Young has a very nice chapter on it. I want to spend at least a couple of weeks to show some models and how we understand magnetism and other quantum effects. But it is going to be towards the end of the semester. And lastly, I mentioned a little bit, but integer and fractional quantum Hall. I think this one I will definitely not talk about it. Integer Hall effect, I had a course on it last year. You can look at it. But fractional quantum Hall effect is much more complicated, and it is a field theory problem because there are strong interactions. But I think this requires a course of its own, so I think if you want that, it won't be in this course. So the main message that I'll try to set up in this course is all of these observations have a great deal in common, right? They are like energy scales are gigantic, 3 to 4 orders of magnitude energy scales, and systems are completely different. In one case, you have like, I don't know, like some mercury liquid, you just cool it down. In other case, you have like helium-3, maybe helium-4. In the other case, you have like a trapped atomic gas. It could be sodium. We are going to talk in the probably second hour. It could be rubidium or potassium. But they manifest quantum mechanics, and we'll see that all of these can be like understood in a kind of condensation. So in the case of a non-interactive Bose gas, we are going to call it like Bose-Einstein condensate. In the case of helium-4, we are going to call it like superfluid. In the case of electrons in a crystal, we are going to call it superconductors, and so on. But these are all, at least they can be perceived from the same perspective. And the technical requirements, like, of course, we have prerequisites like quantum mechanics and things like that, but I will try to make the course quite approachable. Like if you have quantum mechanics and StatMech, that's the only requirement. And we may need to also talk about some techniques like second quantization, path integrals, or functional integrals, green functions, or like Feynman diagrams. But like I said, typically a course like this is based on this technical machinery, right? You spent probably 2 semesters to master all of these techniques because they are very like difficult and they require a lot of time. Calculations are long. But if you do that, you kind of lose contact with physics, unfortunately. So what I'll try is like, I'll try to focus on physics. If necessary, I'll just outline these techniques. If you have the appetite, you can go look at textbooks to learn more. And this is going to be mostly optional. And if people don't like it, I may not do it at all. Good, any questions or any comments?
No, what does it say next to that integral?
Functional integral. So the motto of this condensed matter physics is, nowadays it's not mine and people rely on it a lot, is like so-called more is different. And this is due to Philip Anderson. And I think in the like 50s and 60s or maybe in the 70s, when like quantum phenomena was like generalized to all scales and field theory was being developed, people looked down on condensed matter physics. Like they thought it is like a pesky system and it's not worth spending your time. Like, right? It is like kind of like chemistry. Who cares about that, right? Like cool guys just go and do particle physics, or if they cannot do particle physics, maybe they can try nuclear physics. Not as cool, but still better than condensed matter physics. And the reason is like there was like so many like zoo of effects. People were like thinking it is like kind of like biology. Things were like emerging, right? So this is like emergent phenomena. For example, if you look at Gell-Mann, I think Gell-Mann was one of the opponents of like condensed matter, he didn't think it to be like a respectable field, I guess. But today it is not like this. Today we have like a complete theory that describes all of these things. And the language is like field theory, if you want quantum field theory. And like if you are naive, you may think that like what is more interesting? Like if you are like a purist and you want to understand nature, and the way to go is like you just go to smaller and smaller and smaller, right? When you divide things to like their like most essential, indivisible essence, that must be the truth about nature. That's the philosophy. That was the philosophy. And that's why people like first hypothesize atom, and then a subatomic particle. Atom by itself was like something indivisible, but they divided atom, and there was like subatomic particles, electrons, protons, neutrons. And then they figured that actually proton and neutron are also composite. They are also quarks. And maybe if you look at quarks, they are not actually fundamental at all. There is nothing fundamental at all. There's like a vacuum and fluctuations. And that's the truth about nature, right? That's how we were good. So this is like reductionist mentality. But today we know it is not, it doesn't work like that. When you put many things together, that's actually more complex, and that can give rise to a richer phenomena than like this like reductionist perspective. And the key about is like more particles. That's why you have like many body, or sometimes people call it many particle. When you have many particles put together, they can do a completely different thing that is not explained by their constituents. So you put, for example, in a Bose gas, you put all of these sodium atoms together, and what you see has nothing to do with individual sodium atom. So that's like emergent behavior dominates. And I think before physics, biologists picked up this. For example, if you look at the birds, right? Each bird does just flying, flipping their wings. But if you look at the collection, maybe they have like very nice and flocking behavior that is not explained with single bird. Or if you look at like, I don't know, some biological systems, there are like little things that are doing their own thing, but in the bigger picture, it is irrelevant. And here, I think people also today agree on that for condensed matter. Like there are like a dirty system, like there's like a crystal lattice and electrons and all those things. But when you put them together and if you do the right things, something emerges. And this emergent phenomena is only explained with quantum mechanics. And all of these things, like all of these superconductivity, superfluidity, Bose-Einstein condensates, quantum magnetism, all of these are classified in the realm of emergent physics. But also, like beyond this course, there are also things like, for example, in magnets, in high TC superconductors, there are also things beyond anything I know in particle physics, right? For example, if you are nowadays, if you want to study string theory, right? String theory in the like 70s used to be the candidate for like subparticle physics, and all of these guys, they gave up on that, right? And all of them are today studying condensed matter physics because that's the place that gives rise to, and it's like a supermarket. Whatever you want, you can get from condensed matter physics. And there's like if you're a string theorist, you can study condensed matter. If you are a nuclear physicist, you can study condensed matter because there are like phenomena, all of these things that you can understand in an easier way. I think let me stop here for the philosophical remarks. Maybe we can take like a 5-10 minute break. And when you come back, maybe I can at least introduce Bose-Einstein condensation for non-interacting gas today.